In this video, we'll be learning about Dijkstra's algorithm, one of computer science's greatest hits. Shortest path-finding algorithms have plenty of applications in our everyday lives. For instance, say you'd like the best possible route from your home to the movie theater so you can make it there on time. Another use case would be routing packets along the best possible path in a network. Oftentimes, these paths have a weight or a cost associated with them. You can think of cost as something like toll costs in highways, and in this case, the best possible path would be the one that minimizes the incurred cost overall in your travel. Or the weight can also represent the amount of traffic along the path. So in this case, the best possible path would be the one that saves us the most time. The problem that Dijkstra's algorithm solves is called the single source shortest path problem, abbreviated as SSSP. That is, there is a single source and we find the shortest distance from that source to the rest of the nodes in the graph. Another thing to keep in mind is that the weights of the graph have to be non-negative for Dijkstra's to work. Dijkstra's algorithm repeats the following two steps. First, we greedily pick a vertex u from the unvisited set that has the minimum distance from S. This is called the extract min operation. And next, we relax edges that are coming from vertex u, a step that's called edge relaxation. Let us understand the edge relaxation operation with an example. Say we want to relax the edge from u to v. Initially, the distance from s to v was 10. Now, because of this node u, we now have a chance to update it to 2 plus 3, which is 5, and that is better than 10. So to get a feel of why this is called relaxation, you can imagine the distance from S to V as an elastic rubber band that was stretched to 10 times its original length. Now, we are able to relax it to 5 times its original length thanks to the node U. Say we have the following directed graph with non-negative edge weights. S is the source vertex, and let us calculate the shortest distance from S to other vertices in the graph. The distance from S to S is 0. For the rest of the graph, the distance is initially set to infinity. Now we start the algorithm. Initially, all the vertices are unvisited. We first pick S from the unvisited set since it has the minimum distance, which is 0. We then relax edges coming out from S, namely SA and SB. Let's relax SA first. We see that the current distance to A is infinity and we have a better way of reaching A with a distance of 10. Hence, we update the distance of A to 10. Now, we move on to edge SB. Similarly, we see that the current distance to B is infinity and we have a better way of reaching B with a distance of 5. Hence, we now update the distance of B to 5. So that's how the relaxation of an edge works. We check if there's a need to update the current distance estimate to a shorter distance, and if yes, we update the distance accordingly. We are done with vertex S. Now, we greedily pick the next unvisited vertex with the minimum distance, which happens to be vertex B. We have edges BA, BC, and BD coming out from vertex B. Let us now try to relax the edge BA. We observe that through B, the distance to reach A is 5 plus 3, which is 8, and that is better than the current distance of 10. Hence, we update the distance of A to 8. Similarly, I relax the edge BC. And then I relax the edge BD. Now we are done with vertex B. We then extract vertex D with the next minimum value of 7. We now relax edge DC. Note that we can ignore the edge DS since we are already done with vertex S. So, through D, we can reach C by a distance of 7 plus 6, that is 13, which is better than the current distance of 14. Hence, we update the distance of C. And now we are done with vertex D as well. Next, we extract vertex A that has a minimum distance of 8. We can ignore the edge AB since we are done with B. Now we only have to relax the edge AC. We observe that the distance to reach C through A is 8 plus 1, that is 9, which is better than the current distance of 13. Hence, we again update C to a value of 9. We are done with vertex A as well. The only vertex that's left is vertex C. And the neighbors of C are vertices whose final shortest path distances have already been computed. Thus, we are done with vertex C as well, and that concludes our algorithm. So, here's the pseudocode of the algorithm. First, there's the initialization step. S is basically the source vertex, and we mark the distances of all vertices to infinity, and we mark the distance of S to 0. Initially, the visited set is empty. This visited set contains a set of vertices whose final shortest path distances from the source is already known. This means the moment you add a vertex to this set, its shortest path distance will not be updated in the future. That is, it won't change. And we use a priority queue to implement Dijkstra's algorithm efficiently. Initially, the priority queue will contain all the vertices of the graph. Here, the priority value will be the distance of the vertex from S. And while the queue is not empty, we perform an extract min operation to extract node U. And this basically fetches and deletes U from the priority queue. And we then add node U to the visited set. So this effectively means the distance of U from S will no longer change. And after that, for each neighboring vertex V of U, we basically perform an edge relaxation. That is, we relax U comma V. And here's a pseudocode for the edge relaxation. That is, if we have found a better way to reach vertex V, we basically update it to a better one. So we update the distance estimate to a better one. D of V is set to D of U plus the weight between vertex U and V. And if we are interested in computing the shortest path itself, then we need to do some additional bookkeeping. So we basically maintain a previous array, and here we basically store the predecessor of V as well. That is where V is coming from. And if you do this additional keeping with the help of another array previous, you can basically get the shortest path as well. So that's the only additional thing you're required to do in order to, if you're interested in computing the shortest path. And the rest of the implementation details will be covered in the next part.